All right, another example problem in electrostatics. This time we got 4 charged particles held at fixed corners of a square, side S. All the charges have the same magnitude. 2 are positive, 2 are negative. You got arrangement 1, arrangement 2. All right, so here we go. Let's look at this. First thing we should do is assign some ideas here. I want to call the upper left corner charge 1, the upper right 2, lower left 3, and lower right 4. So 1, 2, 3, 4. Those are our charges. For arrangement number 1, determine the electrostatic potential in the center. So we want to know V there. All right. The V at the center is going to be the V of the first charge plus the V of the second charge plus the V of the third charge plus the V of the fourth charge, all combined. Okay, now something a little peculiar is that even though electric potential, voltage, is a scalar, we have to pay attention to the sign. Positive charges create positive potential, negative charges create negative potential. The equation for electric potential is KQ over R. So all the K is a universal constant. The distance is going to be the same for all of them, and the charge is the same for all of them. So basically, you're going to end up with positive V for the first one, negative V for the second one, whatever it's going to be, positive for the third one, and a negative for the fourth one. So they're all going to end up canceling out and going to 0. So V at the center in this first scenario, V at the center equals 0. Okay, then the next question is the electric field. Electric field. The electric field at the center. Oh, erase that. The electric field at the center. Now, let's see what's going on here. Electric fields. So again, out from positive. So you're going to electric field from 1, from 2 into negative. Electric field from 2. Electric field from 3 is going to be into electric field 3 and out from positive electric field from there. I can tell electric field is a vector. That's all going to be summing to 0. Okay. So electric field at the center equals 0. So for arrangement number 1, potential and electric field are both 0. V at the center equals 0, and electric field at the center equals 0. Everything cancels out. That is not necessarily going to be the case if we start rearranging them. So now the bottom 2 particles are swapped. Here we go. So what happens here? Let's change colors. Let's look at this. So now we've got our 1, 2, 3, and 4 charges here. But notice that 3 was negative. Now 3 is positive, and 4 was positive. Now that's negative. And the questions are the same. What is the voltage in the center? Okay. Again, voltage, electric potential, whatever you want to call it, KQ over R, but it's a scalar. But again, even though it's a scalar, we kind of pay attention to the sign. So you're going to get V1 plus V2 plus V3 plus V4. But like I said, 1 is positive and 2 is now going to be negative. And 3 is positive and 4 is negative, and all the magnitudes are going to be the same. You're going to end up with V at the center still being 0. All right. That's pretty simple. But what happens with electric fields? Electric fields might be different. Let's check it out. The electric field at the center. The electric field is out from 1. The electric field is into 2. The electric field is out from 3. and the electric field is into 4. Ooh, so this is definitely not going to be 0. Okay, we're going to have to add these vectorially. But electric field strength at the center is going to be the electric field from 1 plus the electric field from 2 plus the electric field from 3 plus the electric field from 4. But we're going to end up having to add these vectorially. Okay, now what do we got? What's the first things we need to know? The electric field strength is KQ over R squared. So here we have to do a little bit of arithmetic. We have to figure out what is R. What is R going to be? R is the distance here, right? We'll call this the distance R. That R is going to be half S, that whole thing, right? Squared. So R, if we've got to do that little triangle, half S and a half S, what is that? R squared equals 1/2 S squared plus 1/2 S squared. Right? Boom, boom, boom. Do that. 1/2 S squared and 1/2 S squared is going to be, doing the math, quarter S squared and a quarter S squared is going to be, right, this is 1/4 S squared plus 1/4 S squared equals 1/2 S squared, or S squared over 2. R squared equals S squared over 2, or S times a half. S squared times a half, or S squared over 2. That is going to be over here. So KQ over S squared divided by 2. Or we could say this is 2KQ over S squared. That is going to be the magnitude of each electric field. Okay? So again, we'll get one over here, one over there. So we're going to get 2 of those. 2KQ over S squared and 2KQ over S squared. That's essentially 4KQ over S squared. Why is that going to a silly triangle? And down this way, from out from 1 and into 4, it'll be the same thing, 2KQ over S squared and 2KQ over S squared, or essentially 4KQ over S squared. Add these things vectorially. 4KQ over S squared plus 4KQ over S squared to find their resultant. There's your right triangle, C squared or A squared, whatever you want to call about it. So the C squared equals 4KQ over S squared plus 4KQ over S squared. Before we do anything with that, we can add them up. That's essentially C squared equals 8KQ squared over S squared. Take the square root of all of that. C is going to be the square root of 8 times KQ squared over S squared. And that is the resulting vector. That is the resulting E field. E field equals square root of 8 KQ over S squared. And that's, don't forget this, that's squared. Okay, in a minute. Last part there. Now, in which two arrangement will require more work to remove them? All right, so if we look at it this way, to remove this particle or this particle, which will require more work. Okay, this is going to have an electrostatic attraction there, an electrostatic attraction there, and a repulsion that way. It's going to be attracted by these two there. There'll be an attraction here. There'll be a repulsion there. Why did I do that? There'll be a repulsion there, and there'll be a small attraction that way. Which is going to have a bigger time, a rougher time getting them away? The first arrangement. So for this, both 0. For this one, the V was 0, but the E was the square root of 8 KQ squared over S squared. And for this, arrangement number 1 is tougher because of electrostatic forces. It'll take more energy, more work will have to be done to remove that one than this one.